Do you need GPS in your STM32 project? So today I will show you how to exactly interface the u-blox NEO-6M module that I have to extract real-time location data and parse NMEA sentences efficiently. In our previous video, we discussed about the jargons that are involved in satellite-based navigation systems, available satellite constellations across the globe, and finally we discussed the data sheet of our u-blox NEO 6M based chip. In this video, we will discuss about NMEA protocol, crux of our GPS data algorithm, using Ucenter application to analyze GPS data, and finally we will get our hands dirty and connect the hardware to display our GPS data on the TFT display. Let's first talk about NMEA. What exactly is it? Well, NMEA stands for National Marine Electronics Association. It was originally developed as an interface standard or a quote unquote common language for communication between different electronic systems on board marine vessels like instrument displays, weather sensors, sonar systems, engine monitoring systems, navigation systems, and so on. Even though it originated in the marine world, it has now become a widely adopted standard for GPS-based systems across various industries. Almost every GPS module you come across today talks in NMEA format. But wait, NMEA is not the only protocol available for GPS communication. Yes, we also have binary protocols like u-blox, UBX, and SIRF binary protocol. Speaking of u-blox, their popular NEO-6M GPS module obviously supports both NMEA and UBX protocols. Specific version of NMEA supported is 0183 standard version 2.3. In this video, we shall focus only on the NMEA part. It has two standards right now, 0183 and 2000. The NMEA 0183 standard defines the electrical connections for data transmission as well as data format which is used for communication. A simple way to understand it is through talkers and listeners. So talkers, they usually send data, for example, say like a GPS module. Listeners, they receive data, let's say like a display unit. However, in the 0183 standard, you can only have one talker on a given bus but multiple listeners, depending on the fan-out capability of the circuit. Right now the latest version of NMEA 0183 standard is 4.30, which was released in December 2023. However, the complete documentation is copyright protected and it must be purchased, right? Interestingly, the pricing varies. It is more expensive for consumer electronic industries than for marine related personnel. If you check on the price, you'll probably say, whoa, there is a lot of money just for documentation. The other standard available is NMEA 2000, but it is not exactly back compatible with the 0183 standard. This here supports CAN architecture, thereby making it suitable for multiple talkers and listeners on a given bus. Both of them have different connection standards, and you may read about the standards on the link which is provided in the description below. Here we have a simple block diagram of a generic GPS receiver. Let us break it down step by step. On the left side, we have the antennas that capture the GPS signals. Then we have the power input section. Additionally, if you are using high precision receivers like u-blox F9 or M8 series chips, you can receive DGPS signals or differential signals that provide correctional data, improving accuracy even further. Moving to the right side, we have two main types of output data, NMEA format and proprietary format. So the first one is widely used data format for communication between GPS receivers and other devices. While for the u-blox chip, we have UBX as our proprietary format. And of course, we also have highly precise 1 pps signal, 1 pulse per second. This is a critical output from the GPS receiver as it generates a pulse that is synchronized with accurate GPS time. This pulse is ensured to be accurate even after accounting for any potential timing drift between the receiver's internal clock and the true GPS time. As it can be observed, each message of GPS provides us with some specific information, which is useful in navigation systems. The format for dataset is simple to understand. A $sign indicates start of the dataset. Come on now, dollar even here. GP denotes GPS, followed by initials of respective dataset. Informations are separated by commas, and in the end we have asterisk symbol followed by checksum and carriage return, as well as line feed implying end of our dataset. This is how a data output from receiver looks like. For the sake of this video, we are interested in only two message sets, that is GGA and GSV. The former will give us basic data about our position with respect to WGS84 reference coordinate system. We'll get latitude, longitude, and time with respect to UTC time standard reference. We also get number of satellites that are used in calculating our position or retaining a GPS fix and HDOF. In the later, we get the total number of satellites in our view. Remember our talk on elevation and azimuth in the last series? Yes, we will be getting those values for all the satellites along with the respective satellite ID and SNR for satellites which are tracked by our GPS receiver. We have to note that in one message set of GSV, maximum details of 4 satellites can be received. If we have more satellites available, the number of such consequent messages would be more. So if, say, your total number of GSV dataset is 2, like in this example, your current number of GSV dataset will be 1 and 2, and both of these messages will be transmitted one after another. Similarly, if you have, say, 13 satellite data to be displayed, total number of GSV dataset messages that would be sent will be 4. How, you ask? Simple. Maximum 4 satellite details at one time multiplied by 3 such message datasets gives us 12 satellites. And in our last message set, only 1 satellite detail would be present. Hope it is clear. If not, just replay the section. Let us now talk about our STM32 board. So the reference ID of this particular Devkit we have is ST25R3916 Disco. And this is basically for RFID and NFC based applications. The green bottom part is the RF antenna and RF chip, while the top part has STM32L4 based chip and TFT display. So I thought to use the top part with the TFT display to give us a better visual output of our GPS data. To find out more about the specific pins, we will refer the schematic. We have multiple sheets in the first page of the schematic, and for the UART pin, we will go through ST25DX_connector sheet. So basically UART pin is at the upper section of the top board pins, and the connector we are interested in is J6. Relating those pins back to the STM32L476 sheet, we get PD6 and PD5 as our USAR2 peripheral receive and transmit pins respectively. Alright, let us quickly go through our block diagram. We have our main L4 based MCU and TFT display on the board. Next we have taken USB to TTL based converter to record the data. u-blox NEO-6M is connected to both dish devices, and this is just for purpose of analyzing data simultaneously and not at all recommended for regular use cases. So the Devkit only receives data from the receiver while the TTL module receives as well as transmits. We are powering the receiver from the Devkit onboard supply. Next stop, STM32 cube ID. We have our main project already prepared, and we will open up our IOC file under the connectivity section. We'll set up USART2 in asynchronous mode along with the baud rate set to 9600. Next, the global interrupt is turned on and DMA is not used. The GPIO involved is already known. Time to talk about NMEA message sentence parsing. So our USART peripheral is operating in interrupt mode, wherein after every byte received or every ASCII character received, an interrupt occurs, and we eventually save that particular data in our GPS buffer. Each character or byte of that data in the GPS buffer is represented by a square block here. Two of the index variable head and tail are used. Let us explore what they actually represent. Okay, sorry, wrong video got mixed up. So head and tail are index buffers, and the former updates its value when new data is available to write in the GPS buffer, while the later updates itself when data is read from the GPS buffer. When the GPS buffer is empty, both of these indexes are initialized to 0. Let us take an example of GGA dataset. The first character available is $, which will be appended to our GPS buffer, thereby incrementing head index. Similarly, all other characters are written but keeping head just before tail and not equal to it, so as to avoid rewriting of the same data before analyzing it. Simultaneously, a function peeks into this GPS buffer and searches for the interested dataset GGA or GSV, in our case, character by character. This causes the tail index to increase as well. If dataset character matches all along, we copy the sentence related data from the comma next to the dataset identifier until the asterisk symbol explained in the data format section earlier to a completely new buffer. Then, through some careful function manipulation, the useful info is extracted. Mind you, all of this is happening at a very high rate. So, back to our cube ID. This is our main code here, and in the beginning we have some TFT display based greeting messages and images. In the main while loop, we can see find dataset function, which is responsible for checking out if the sentence is available or not. If yes, save dataset function is called and another buffer is saved up to asterisk symbol. Next, info is extracted from those saved dataset buffers, and in case of GGA we return GPS valid fix, while in case of GSV we return total satellites available. On receiving the satisfactory values, information is displayed on the TFT screen in a particular format. Okay, we have accumulated all of our components now together. That is STM32L4 based Devkit with TFT display, u-blox NEO-6M GPS receiver with ceramic antenna, a USB to TTL module, small breadboard for connecting wires to route, a mini USB to USB type A cable to connect our Devkit with our PC, and some wires. After connecting the hardware, as specified in the block diagram earlier, we are ready and it's showtime. On our PC, we'll open a serial terminal Hercules and select the correct COM port representing TTL module. After selecting the correct baud rate, we will observe that data is continuously transmitted from the receiver end. There is no way to make it stop. Right now, due to cold start, GPS fix is not yet attained, and hence the data is not exactly in the specified format. You can still observe the starting $character with the initial GP followed by the message initials. Now opening Ucenter Application, we have with ourselves a certain GUI of the available data. Navigating through this app is not much difficult. On the left side of the screen, we will select the COM port of our TTL module. Next, under the View tab, select Configuration View. Then, in PRT port section, you can change the baud rate as per your needs. After selecting the desired rate, click Send on the bottom left corner of the screen. Now disconnect your port from Ucenter and let us once again open up Hercules terminal and check if the baud rate really got updated. Alright, selecting the port, connecting, and yes, it is updated to 115200 successfully. Now to connect back on Ucenter, disconnect from the serial terminal and go to Tools tab. Under baud rate, select 115200 and woohoo! You are connected. You may have a look at all of the other settings if needed. After waiting for a while, we have attained the GPS fix in our room. On powering up, we see a Namaste and welcome message. Witness the blinking blue LED on board GPS module. The location and satellite details are now available. Let's take this setup and watch the sat count in open sky. Alright, so I have moved the needed components to terrace. After setting it up, we are good to go. Before, let me just show you the vibes here. The sun is about to set and the greenery, it is all around us. Amongst them lies our setup right there. On powering up our system, we are getting 6 satellites in the beginning of our GPS fix. Let's open our Ucenter application and connect our module to analyze our data further. Under View tab, select Messages View to look out at the decoded data from sentence of respective dataset. So as time passes, the sat count increases to 10 and then 13 tops. Don't worry about the TFT display part, we will be discussing it in upcoming video. That is it from my side in this video. I'll be packing up and probably watering my plants. Please support this channel and subscribe. And yes, don't forget to like and share this video. In our upcoming video, we'll try to have a look at the datasheet of our TFT display and understand how to work around with the TFT driver and display images as per our choice. Signing off.